I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
Hi, I'm Julie Stopar. I'm a lunar scientist at the Lunar and Planetary Institute in Houston, Texas. In the course of this presentation, I'll discuss the events that have shaped the moon's surface or crust. I'll also touch in this discussion on how our knowledge of the surface has changed as we have received new information and new images like this one. This is a Lunar Reconnaissance Orbiter camera image of the dramatic landscape of the Apollo 17 landing site. In the center of this image is the low-lying Taurus-Latrobe Valley. It has been partly flooded by ancient lava flows. The valley is surrounded by the mountainous peaks of the moon's highland terrain. And this valley is a great example of where we can see contrasting landscapes merge on the moon. From exploration of the Taurus-Latrobe Valley, we've seen the results of the major geologic forces that have shaped the moon's surface. In this image, for example, you can see small impact craters that dot the floor of the Taurus-Latrobe Valley. There is also a fault that arches across the central portion of the valley, and products of ancient impacts are eroding out of the valley's walls. The surface of the moon is heavily cratered, and it was partly flooded by lava flows over 3 billion years ago. And while the most dramatic events have occurred early in the moon's history, it is still an active geologic body today. For example, meteorites continue to bombard the surface. Impacts by comets and asteroids continue to grind up and wear down this outer surface. These impacts are creating an upper layer of debris called regolith. This layer consists of rocks and soils, and it covers nearly all of the outermost surface of the moon. Regolith is actually what the Apollo astronauts interact with during their time on the surface. This is an image of Charlie Duke, one of the Apollo 16 astronauts. He's using a rake on the lunar regolith in order to collect small rocks. The moon has a near and far side. One difference between the near side and far side is very noticeable. The near side is dominated by dark, low albedo MARE areas, which are made up of ancient basaltic lava flows. The far side, however, is dominated by bright cratered highlands. Our first glimpses of the far side came from early spacecraft. Luna 3 in 1959 was the first, followed by others, including Lunar Orbiter 3 in 1967 and Sonde 8 in 1970. And the first human eyes to directly see the far side were those of the Apollo 8 crew in 1968, as they looped around the far side of the moon. This is what they saw. It's a densely cratered terrain. Today we have many wonderful new mosaics of the near and far sides of the moon. These mosaics are derived from recent spacecraft data, primarily coming from JAXA's Kikuyu spacecraft as well as NASA's Lunar Reconnaissance Orbiter. Also included in this amazing dataset is a narrow-angle camera mosaic of the North Pole. This mosaic extends from the pole to 60 degrees north latitude. The mosaic is sampled at a scale of 2 meters per pixel and includes more than 10,000 individual narrow-angle camera images. Shown here are a few examples of what you can find in this mosaic. There are many young impact craters, and there are also regions of irregular low hills and hummocks, which are typical of large impact melt deposits. There are also faulted and folded volcanic plains, and you will also find chains of collapsed pits. There are mountain peaks at the poles which cast long shadows. This is a result of the low sun angle. The shadows accentuate the shape of the terrain at the poles, and the sun is always low on the horizon, so there are always many shadows. These mosaics were made from images that were acquired when the greatest amount of the surface area was illuminated. That means they were acquired during the summer season at each pole. When the sun is high overhead, as in the mosaics shown here, mountain peaks and valleys become harder to see. Variations in morphology become more difficult to discern. But when the sun is high overhead, variations in albedo and color become more clear. Albedo is essentially the amount of reflected solar illumination from the surface. The low albedo lava flows that dominate the near side, as well as sprinkled parts of the far side, are very distinct against the bright cratered highland terrains when the sun is high in the sky. Bright streaks and rays, also seen radially distributed from bright young craters, are very distinct. Some surface features are very prominent on the face of the moon. For example, Aristarchus crater is a 40-kilometer diameter impact crater. It's also the brightest feature on the near side. Tycho crater is about 80 kilometers in diameter, and its bright rays dominate the southern near side. One of the most prominent bright rayed craters on the lunar far side is Jackson. It's a 70-kilometer diameter impact crater. Actually, impact craters come in all sizes, and the shape of the crater depends on its size. Jackson, Aristarchus, and Tycho are all examples of complex crater forms. These craters have a mountainous central peak inside the crater. Their walls are scarred with the terraces and slumped portions of rock. And the floor between the peak and the walls is relatively flat to hummocky and filled with debris and impact melt deposits. As I said, impact craters come in all sizes. They range from huge impact basins greater than 200 kilometers in diameter, down to small pits that are only revealed by a microscope. Simple or bowl-shaped craters, as they are sometimes called, are the smallest craters we can observe from orbit. Simple craters are typically less than 15 kilometers in diameter, and they lack the central peak and other uplifted structures seen in complex craters. A simple crater's walls are steep, and they do not have terraces either. These craters overall have experienced much less slumping into the crater floor than their larger counterparts. Simple craters do have a raised rim, as do complex craters, and you can see it in this side-looking view of Simple Crater in the Lunar Highlands. This crater is 9.3 kilometers in width, with a rim that rises about 400 meters above the surrounding surface. This rim height is created by both ejecta as well as rocks in the impact zone that have been displaced or injected into the surrounding terrain. At crater diameters between about 12 to 18 kilometers, morphologies of the craters become more transitional between the simple and complex types. In this transitional size range, craters can exhibit some or none of the characteristics we see in complex craters. The impact cratering process begins with an impacting object, like a meteor or comet, colliding with the moon. The relative velocity of the impact is typically many kilometers per second, with the average being about 16 kilometers per second. The force of this impact sends a shock wave through the target and back through the projectile. The shock wave then compresses the surface radially, creating an immense pressure regime. The pressure is released as a rarefaction wave, which expands upward and outwards when it reaches the surface. In this process, most of the impactor itself is vaporized. Some of the target's surface is also vaporized as well. The crater cavity is excavated as target material is displaced, and near-surface material moves upward along the edge of the cavity and then outward as a curtain of ejecta. Deeper material is actually displaced downward into the crater. The ejecta is sent on a ballistic trajectory, landing radially outward from the crater. And any ejecta traveling faster than the escape velocity, which is about 2.4 kilometers per second, will be lost to the moon. When the shock wave in the target stops expanding, the crater will stop growing. This all happens within about 10 seconds to a few minutes after the impact. After excavation, the crater cavity will adjust to local gravity and material strength. At this point, the unstable wall materials will collapse into the crater, and in complex craters, this is when the central part of the crater rebounds to uplift the floor and form the central peak. This modification process may only last a few more minutes. Rocks found in and around the crater are highly fractured, and they form a rock type called breccia. The crater deposits can also include rocks that were melted during the release of the extreme pressures experienced during the impact event. So debris landing within 2 crater radii from the crater's rim will form a continuous ejecta layer that mixed in with the local materials around the crater. This forms what we call the bright continuous ejecta, and this is seen around young craters. At greater distances, the ejecta incompletely covers and mixes with the local materials, and these more distant areas are typically referred to as the discontinuous ejecta layer, or deposit. New data and crater studies enabled by LRO now reveal that an impact crater disturbs the surface for hundreds of radii away from the primary crater, and that's actually many times farther than we previously suspected. Larger bits of ejecta and debris moving with enough velocity will form a new small impact crater. These are called secondary craters. These craters form with much lower impact velocities than do primary craters. They're most frequently found within 2 to 5 diameters of the primary crater, and they're less than about 5% of the primary size. Secondary craters have asymmetric shapes and chevron-shaped ejecta patterns. These patterns point like arrows back to the source. Secondary craters like those you can see in this image here probably impacted at a relatively low angle to the surface between about 30 and 45 degree angles. The low angles and low velocities that typify secondary impacts contribute to their asymmetric shapes and ejecta patterns. So now let's explore the volcanic areas and how they are related to impact features. The major nearside volcanic maria include Oceanus Procellarum, Mare Imbrium, Mare Serenitatis, and the Mare Tranquillitatis, Crisium, Fecunditatis, and Nubium. Many of the nearside maria fill basins carved out by the much older impact events. So in the northern hemisphere on the far side, we see a dot that marks Mare Moscoviense. The southern far side is dominated by a mottled dark region, which we call the South Pole Aegean Basin. This is an ancient impact basin roughly 2,500 kilometers across. This view, looking north from the south pole of the moon, really illustrates the enormity of the area that is affected by the South Pole Aegean Basin. The interior of this basin is dotted and pockmarked with dark volcanic mare deposits. Of course, the surface of the moon has not always looked the way it does today. We think that before about 3.8 billion years ago, the moon was actually dominated by the scars of impacts, but there were very few volcanic plains at that time. Notice the difference in how Imbrium Basin, Serenitatis Basin, and Crisium Basin would have looked. Early on, the moon was covered with a bright and north-acidic crust, and into this bright crust, the large basins were formed. Partial melting of the moon's interior that led to the volcanic eruptions occurred long after basin formation. However, the basins actually helped to guide where those volcanic eruptions would eventually occur by forming many fractures in the lunar crust. Many volcanic eruptions have occurred along the basin margins and at intersections of basins where the most fractures would be concentrated. And these fractures provide pathways for lunar magma to reach the surface. We think that most of the Mare eruptions occurred between 3.8 and 3 billion years ago. These eruptions flooded the lower lying areas of the ancient basins, now infilling Imbrium, Serenitatis, and the others. We think that some of the volcanic eruptions might have continued until about 1 billion years ago. However, this is still uncertain because we do not have ages for many of the maria. We can, however, try to estimate their ages based on the sizes and numbers of craters found on their surfaces. And this is a technique that many people refer to as crater counting. However, this technique has many uncertainties, and particularly for young surfaces, it lacks ground truth. Nonetheless, we still think that by about 3 billion years ago, the moon would have looked very much like it does today. For years, the CLEMENTINE Global Ultraviolet Visible Spectrometer dataset provided the standard reference for our understanding of the composition of the moon. The CLEMENTINE data are frequently used to enhance differences on the surface related to soil mineralogy, grain size, and degree of space weathering. So this means that green colors here largely reflect iron-bearing minerals found in igneous rocks, while blue colors at least in part, reflect the titanium content. So titanium can also be found in volcanic rocks along with iron, and is primarily found in a mineral called ilmenite. The red colors here largely reflect the amount of space weathering, which reflects the accumulation of iron-bearing and glassy products over time. These products are agglutinates and submicroscopic iron, and these products are formed in the lunar soil as it's exposed at the moon's surface. With the MARE rich in iron and sometimes titanium, and the highlands poor in both of these, the CLEMENTINE data really show differences between the MARE and highlands very clearly. In this color space, the MARE appear teal and yellow as a result of the iron content, while high titanium MARE deposits like those in Mare Tranquillitatis appear to bright blue. Ancient highlands, on the other hand, appear magenta to red, and more recently exposed highland materials found in young impact craters appear blue. Following on the heels of CLEMENTINE, the Lunar Prospector mission provided global views of certain elemental abundances, notably iron and thorium. These abundance maps were derived from gamma-ray spectrometry. The thorium map still remains the standard for tracking thorium-rich compositions in the outer crust. And from the maps, we can see that thorium is concentrated on the near side. This is an area known as the Procellarum creep terrain. It is also an area where we find a large concentration of MARE. The enhanced thorium, which is a radiogenic heat-producing element, is likely tied to a longer duration of volcanic activity here. So the far side is dominated by cratered highlands and has relatively little thorium. There is, however, one large circular compositional anomaly on the far side that does show a slight enhancement of both iron and thorium. And this area is the South Pole Aitken terrain. We think the thorium in this area is related to deep crustal or mantle materials which were brought near to the surface by an ancient impact basin event. Compositional information now comes from multiple additional instruments, including the Moon Mineralogy Mapper, the Multiband Imager, the Diviner Radiometer, and the Lunar Reconnaissance Orbiter wide-angle camera. These data represent many different ways of looking at the surface, and each of them tells us something different about the moon's geology and its history. In addition, we also have several new topographic models that were derived using data from LRO and the Kaguya spacecraft. These new models represent yet another major advance in information about the moon. Topography and morphology, when used along with other information like composition as well as gravity, tell us about how things formed as well as their structure. The elevation in these models is reported relative to a reference sphere. It has a radius of 1,737 kilometers. And the moon's global elevations range from about 9 kilometers below this reference to 11 kilometers above. The range that we see is very similar to the range in elevations that you can find on the Earth, ranging from the lowest seafloor to the highest mountain peak. And both of these points are actually found on the far side. The lowest point is found inside the South Pole Aitken Basin. The highest elevations are found on the moon, where the crust is the thickest. The far side crust is up to 60 kilometers thick in some areas. Large impacts into the early moon formed basins and built up a rugged terrain of fractured and brecciated crust. And it's probably not a coincidence that these highland areas have very few MARE deposits. The thicker crust here makes it much more difficult for magma to rise to the surface. Instead, the greatest expanses of volcanic MARE deposits are seen where the crust is relatively thin. The MARE were formed by floods of lava, and they are great lava plains. The typical surface slopes of the MARE are less than 3 degrees on average. For comparison, slopes are 10 degrees or more in many of the highlands areas. Individual MARE flows may be hundreds of kilometers in length and range from 1 to tens of meters thick. This image here shows some very distinct lava flows that you can see in Mare Imbrium. These flows were imaged from orbit during the Apollo 15 mission. The low sun angle of this image helps to reveal the margins of these flows. However, while these flows are very distinct, most MARE flow boundaries are not this apparent. We do have some information about low albedo layers, which are exposed in the walls of craters formed within the MARE. These layers are only a few meters thick, and they appear as bands within some crater walls. The layering suggests that the MARE deposits consist of thin emplacements of lava that are built up over time. However, even though we have this information, we do not yet know what the sources are for many of the lava flows. The sources are apparently obscured or unrecognizable. Perhaps they've been buried by lava during the eruptions. In contrast, some MARE deposits appear to have very clearly originated from sinuous rills and lava channels with elongate source vents. These vents produced enormous fountains of lava, and individual eruptions might have continued for years. For example, on the Aristarchus Plateau, the rill here is named Valles Rotary, and it winds for about 125 kilometers across the plateau. This rill is up to 4.5 kilometers wide, and in some places up to 400 meters deep. The head of this rill may be one of the source vents for the vast MARE deposits that we see to the west in Oceanus Procellarum. When eruptions are lower in volume, small lava shields can form around centralized vents. Small shield volcanoes on the moon are generally less than 30 kilometers in diameter. The ones shown here in this image are located near Hortensius crater. And these particular shield volcanoes range from 5 to 10 kilometers in diameter and up to 200 meters in height. Most of the shields here have a central crater that is likely the source of the main eruptions. These central craters lack the raised rim that's typical of impact craters, and they're also more elongate in shape. However, many shields and some dome-like structures on the moon do not have such obvious central vents. And these landforms may have resulted from uplift caused by near-surface intrusions of magma. This is magma that did not erupt onto the surface. While most volcanic shields on the moon are less than 30 kilometers in diameter, there are some regional areas of volcanic activity which has resulted in much larger and broader rises. One example is Mons Rumker, which is shown here. Mons Rumker has multiple source vents across the shield, but no obvious central vent or summit caldera. On the Earth, summit calderas are typically found at most shield volcanoes. They signify a near-surface magma chamber that has periodically erupted and collapsed cyclically. Lunar volcanoes, on the other hand, are thought to be sourced directly from deep magma sources. On the moon, there have also been eruptions of pyroclastic ash and glass. These eruptions form broadly distributed, low albedo mantling deposits, which we often call dark mantling deposits. They form a thin blanket of pyroclastic materials draped over pre-existing terrain. Some dark mantling deposits are very broad and regional in scale, like those seen near the Apollo 17 landing site. At Shorty Crater, along the second traverse of the Apollo 17 mission, astronaut Harrison Jack Schmitt discovered orange soil by his feet. He dug a trench into the wall of Shorty Crater to get a sample of the orange glass and some of the black, partly crystallized glass beneath it. Here you can see part of soil fraction number 47220, which contains small 150 to 250 micron sized grains. These grains were recovered from the center of the trench. The returned materials are traces of a very large pyroclastic deposit to the west. This pyroclastic deposit covers about 4,000 square kilometers. You can see where dark materials overlie in mantle portions of both the low-lying, relatively flat MARE deposits as well as the upland highlands areas. Other lunar pyroclastic deposits are localized, and they form small deposits along a fracture or fault, like these examples found in Alphonsus crater. These dark patches are each about 10 kilometers in diameter, and they have a deep central crater that is likely their central vent. Explosions of gas likely occurred along much of the faults seen within this crater. The deposits themselves typically contain less glass and more rock fragments than their larger pyroclastic counterparts. The rock fragments, we think, are generated during explosive eruptions in the near surface, which fragments the country rock. While most of the volcanic activity on the moon is basaltic in composition, we do see a few examples of more evolved rock types on the surface. There are about a dozen irregularly shaped volcanoes that were formed by eruptions of more silicic compositions. This is magma that has more silica and less iron than basalt. Early in the LRO mission, the newly produced global topographic models eventually led to the discovery of a large silicic volcanic complex within the highlands. This area is now known as the Compton-Belkovich Volcanic Complex. It is a broad shield that rises about 25 by 35 kilometers across. It was in fact actually quite a surprise to find such a large silicic volcano outside of the Procellarum creep terrain and within the highlands. And this discovery signifies that we still do not fully understand the magmatic and crustal processes required to produce large volumes of silicic magma on the moon. Lunar scientists will continue to use the new topographic data as well as gravity models to find and continue to characterize additional volcanic landforms. These activities will help us gain further insight into volcanic eruptions over lunar history. So far we've talked about impacts and volcanism, so now let's explore tectonic landforms. Both the moon's volcanic landforms as well as the cratered terrains have been reshaped by later tectonic forces. The crust of the moon is deformed and faulted in many places. Compressional forces result in landforms including thrust faults, wrinkle ridges, and scarps. Wrinkle ridges, for example, are found in all of the major MARE terrains. The map here shows the distribution of wrinkle ridges on the near side. The ridge shown here on the right is located in MARE Imbrium, and it's about 400 to 900 meters wide. Wrinkle ridges, however, can extend for hundreds of kilometers. On the other hand, extensional stresses form normal faults and graben. These landforms cut across the highlands and MARE deposits. Shown here is Rima Ariadeus. This is a graben that's about 4 kilometers across and it stretches for over 250 kilometers through the nearside highlands. While compared to the Earth, the moon is tectonically quiet, it is in fact, however, still shrinking. The moon is still continuing to cool and contract, and as it does so, the crust of the moon is compressed in many places. Thanks to the new data from LRO, we now think that over the last 100 million years or so, the moon has gotten about 50 meters smaller. And of course, some faults are still periodically active, causing moonquakes. And as more data and images are returned from LRO, we can now observe contemporary changes occurring on the lunar surface. These are changes and events that happened within the last 10 years. To find them, what we do is we compare older images with newer images of the same location. And by doing this, we have discovered that hundreds of new impact craters have formed since LRO has been in orbit. And these new craters often correlate with bright flashes that have been observed from the Earth with telescopes. The one shown here was observed as a flash from Earth on September 11, 2013. This crater was imaged several months later by LRO as the spacecraft passed over the impact location. And by looking for new impact craters like this one, we're learning more and more about the current impact rate on the moon. And we are finding that it is significantly higher rate than we previously thought. New data and images from LRO and other recent spacecraft are providing unprecedented views and information about the surface of the moon. So while some scientific questions have been answered, others yet remain, and some of these questions remain to be answered by renewed surface exploration. And as we continue to receive new data from LRO and other future spacecraft, as well as surface explorers, we will no doubt continue to reveal surprising new discoveries and insights about our nearest neighbor in the sky.